Let's jump right in. Look up at the sky and you probably just see clouds, right? But for aviators, that same sky is an invisible, ever-shifting battlefield. It is literally a maze of pressure, moisture, and hidden energy. So welcome to today's Explainer, where we're going to decode the exact tools and data that pilots and meteorologists use to actually navigate these invisible hazards. Okay, let's kick things off with a massive mythbuster. When a pilot checks their weather radar, they're not actually seeing wind or turbulence. Nope, they're seeing moisture. See, radar works by blasting out a pulse of radio energy and waiting for it to bounce back. And here's the wild part. Water is literally 5 times more reflective to radar than ice is. Because that return signal completely depends on the size and density of the particles, stuff like wet hail and heavy rain, they absolutely light up the screen. Meanwhile, dry snow or even pure wind shear remain pretty much invisible. Here's our flight plan for this explainer. We'll start with the big picture, then move into seen through storms, take a little detour through southern African weather, and wrap up with some legendary local winds. Let's get into it. All right, part 1, the big picture, and how forecasters actually map out the sky. Long before a pilot even steps foot on a plane, forecasters are already mapping out the atmosphere using standardized upper wind and temperature charts. Now, these follow super strict international rules, like ICAO Annex 3, and they use very specific global map projections. They slice the sky at precise pressure altitudes, going from 10,000 feet all the way up to flight level 530. Oh, and here's a crucial rule of thumb if you're ever looking at one of these. At those extreme altitudes, temperatures are always assumed to be negative unless you specifically see a plus sign. Now, to pinpoint massive, high-altitude jet streams, meteorologists can't just rely on your basic surface charts. Instead, they use multi-spectral satellite imagery to track something called atmospheric motion vectors, or AMVs. Basically, by watching clouds or even invisible water vapor move across a sequence of satellite images, they can track those high-speed winds way up aloft. It's kind of like adding flesh to the bare bones of low-level frontal charts, so you can see exactly where the weather is acting up, both in front of and behind the actual frontal line. And when a really immense, swirling threat is brewing out there, the aviation world needs a universal language so everyone is on the exact same page. Enter the Tropical Cyclone Advisory Service, or TCACS. They use this globally standardized 19-element format. When these advisory centers put out their text and graphical updates, every single line has an exact, non-negotiable meaning. From DTG, meaning the date and time group in UTC, all the way to MOV, which tells you the cyclone's movement direction and speed across 16 compass points. It's a system literally built for absolute clarity. No room for misunderstandings here. Okay, moving right along to Section 2, seeing through storms, or basically having X-ray vision in the cockpit. So let's transition from that calm pre-flight briefing room right onto the flight deck. This is an intense, tactical environment where making a split-second decision based on bouncing radio energy can literally keep you alive. And the crucial thing to understand here is the massive difference between ground radar and airborne radar. Ground radars link multiple stations together to give forecasters a really wide area picture. They're mostly looking for low-level, heavy rainfall. But the radar inside the airplane, it has a much more vital, focused job. And that job is avoidance. It's not there to measure rainfall for farmers. It's there to help the crew steer clear of thunderstorms and all the terrifying stuff that comes with them, like severe turbulence and massive hail, right along their exact flight path. Now, if you look at the color coding on a pilot's navigation display, it usually goes like this. Green means weak moisture, amber is medium, and red means heavy moisture. Some newer systems even throw in magenta to highlight turbulence using Doppler radar. But here is a massive warning. Red doesn't automatically equal turbulence. Red just means you've got a really dense wall of water. The actual danger, like the truly violent plane-shaking turbulence, tends to hide right at the edges of a storm cell. Pilots are explicitly trained to hunt for areas where the green, amber, and red zones are squished really tightly together. That tight gradient means the air and moisture are changing rapidly, and that practically guarantees a violently bumpy ride. But it's not just about the colors. Pilots are reading shapes too. Take a look at these hand-drawn sketches highlighting some genuinely menacing cloud shapes you might see on a display. If that radar return has scalloped edges or weird little fingers extending out from the main cloud, or if it forms hook shapes or U-shaped cavities, well, those are massive red flags. Every single one of those twisted shapes is a dead giveaway for an intense, dynamic thunderstorm, packing catastrophic hail and crazy updrafts. However, relying purely on what the screen tells you can be a fatal mistake. Pilots have to constantly watch out for a really terrifying illusion known as radar shadowing. Let's break down how this actually happens. First, the plane's radar pulse hits a storm cell that is absolutely packed with water density. Second, because there is just so much water, the radio signal undergoes extreme attenuation. In plain English, it gets completely absorbed and weakened. Third, because the signal can't push through that wall of water, the violent storm lurking directly behind it gets completely masked. The display just paints a false black, clear zone. You can see how dangerous that is, right? A pilot might think they're turning into a safe, clear alleyway, but they're actually flying directly into the hidden, violent core of a massive thunderstorm.
All right, part 3. We're doing a geographic case study focusing on southern African weather.
So let's zoom out from the cockpit for a second to a sort of geographic boss level to see how giant overarching pressure systems dictate hazards for an entire region. Southern Africa is basically sliced right down the middle by a subtropical high-pressure belt. Now, in the summer, a thermal low-pressure system completely dominates. You've got the Indian Ocean high pumping this warm, incredibly moist air over the east coast, bringing massive summer rainfall and those huge convective clouds. But wait for winter, and the script totally flips. Massive high-pressure systems link up over the interior of the continent, creating subsiding, descending air that acts like a giant lid. It just squashes any warm air trying to rise, completely killing off convection. That leaves things incredibly stable and dry, which lets westerly wind waves, or cold fronts, migrate up north, causing these really sharp temperature drops as polar maritime air sweeps on shore. Which brings us to our final section, legendary local winds. These are the true weather monsters. Let's meet a few of these hyper-localized weather monsters spawned by those massive continental pressures we just talked about. First up, the southwesterly buster. If you ever happen to be flying, or sailing for that matter, near the KwaZulu-Natal coast when a low-pressure system is passing by, brace yourself. Since the wind around a low pressure moves clockwise and the whole system is trekking east, the wind suddenly snaps onshore. It creates this violently sharp 180-degree change in wind direction that catches a lot of people totally off guard. Then, of course, you've got the famous Cape Doctor. This thing is a powerful, relentlessly persistent southeasterly summer trade wind. It's driven by a band of high pressure sitting to the south, and it can howl anywhere from 10 to a jaw-dropping 70 knots. It's actually legendary for slamming into Table Mountain and creating that absolutely iconic tablecloth cloud that completely drapes over the ridge. Now, whatever you do, don't confuse the Cape Doctor with the Black Southeaster. The Cape Doctor is mostly a dry summer wind, right? But the Black Southeaster is a whole different beast. It's driven by a deep low-pressure system violently clashing with a steep pressure gradient off the South Atlantic high. That steep gradient basically forces the wind, while the low-pressure system drags in deep, miserable, soaking rains, usually hitting during the spring and autumn. And our final phenomenon today is the berg wind. This is the South African term for a phone wind. Basically, air rotates anti-clockwise around a high-pressure system sitting up on the elevated interior plateau. As that air gets shoved off the plateau and starts plunging toward the coast, it compresses. And as it compresses, it warms up incredibly fast. It literally heats up like a giant oven, just blasting the coastal areas with dry, intensely hot air, which ultimately creates a coastal low. Wow. After seeing exactly how aviators have to decode these invisible atmospheric battlefields, from dodging completely hidden storms behind radar shadows to anticipating how giant pressure systems can just spawn 70-knot local winds out of thin air, it really changes how you look up at the sky, doesn't it? It kind of makes you wonder about the hidden mechanics, the pressures, and the unseen moisture secretly shaping the weather right outside your own window right now. Anyway, thanks so much for joining me for today's explainer, and hey, keep looking up.